In the previous videos, we saw the basic topology of the H-bridge inverter and how pulse width modulation is used to control the inverter output. In this video, we will see how inverters are practically configured. More in detail, we will have a look at the configuration of inverters without transformer or transformerless, and at the inverters that implement a transformer either at low or at a high frequency. In the end of the video, a comparison between the three types of inverter will be provided. Nowadays, most of the new string inverters are designed without a transformer. We are going to see why and what is the difference between a transformer-based and the transformer-less concepts. First of all, the PV system needs to be connected to ground, and it is equipped with an earth fault monitoring system, which is able to detect any fault at the DC side of the inverter. An EMC filter is connected at the input of the inverter. EMC stands for electromagnetic compatibility, and it represents the ability of the electrical device to operate without being affected or causing electromagnetic interference. After the filter current and voltage are measured, and the data is sent to the maximum power point regulator. In order to keep the PV array at the maximum power point, a boost converter is provided to step up the voltage at the DC side. The boost converter is used because the DC voltage must be around 370 volts in order to supply the grid with the 230 volts in AC. The signal to regulate the duty cycle of the converter is determined by the maximum power point tracking algorithm. In order to smoothen the output signal of the boost converter, a DC link consisting of a shunt capacitance is used. The following part of the inverter is represented by the pulse width modulation bridge, which is the essential part of the inverter, as we have seen in the previous lectures. This part features 4 switches that convert the DC voltage input into a 50 Hz sinusoidal voltage ready to be fed into the grid. The PWM bridge itself is connected to a central controller that determines the pulse width of the output. The residual current measurement is connected to the grid monitoring, and it is used to detect the presence of any undesired residual current flow into the lines. After this part, circuit breakers are usually present in order to shut down completely the inverter in case of overvoltages or voltage dips on both the PV and grid sides. The breakers are linked to the grid by means of a grid monitoring system so that they can be activated when faults occur. In this case, voltage, current, and frequency are the parameters normally included in the data exchange. Then another filter is present at the grid side. As for the EMC filter at the DC part of the inverter, this filter too is used to make sure that neither the grid nor the PV array see any high-frequency distortion in the power signal. Finally, the output of the inverter can be connected to the grid, generally at around 230 volts. All the control and monitoring systems that we can find inside the inverter are connected between each other through a data bus. The data bus is then connected to a data interface, which is normally a screen on the chassis of the inverter. Alternatively, the data can also be stored in a web server for web-based applications. Among the information that the data bus is able to provide to users, we can have the instantaneous power, the energy generated by the PV system and transferred to the grid, and so on. Now we will look more closely at the inverters that instead feature a transformer and discuss their advantages and the disadvantages. All initial string inverters were equipped with mains transformers. The main reason was that the PV generators were designed only for safety with a voltage level of maximum 120 volts. Also, galvanic isolation was a priority feature for personnel safety. Besides this, as we will see more in detail, 50 Hz transformers only show disadvantages. Let's see an example of an inverter with a transformer. Here, the PV string delivers 100 volts in DC that needs to be converted using, again, a pulse width modulation bridge topology. The peak-to-peak voltage is obtained from the chopped signal is 200 volts, since, as we have seen in the previous lecture, the pulse waves that the PWM bridge produces go from plus to minus the input voltage. Considering the fundamental harmonic of the output wave, we obtain an effective voltage of approximately 70 volts. This is not enough to be fed into the grid, therefore a transformer is needed to step up the voltage level to the desired 230 volts level. As an alternative to the 50 Hz transformer, a high-frequency transformer can be used to provide galvanic isolation between the DC and AC sides. Since the frequency is higher, the transformer can also be smaller and therefore cheaper than the main transformer. To have a global comparison of the three types of inverters seen so far, let's have a look at the table shown in the screen. One of the main aspects to take into account when it comes to choosing an inverter is the galvanic isolation. Galvanic isolation enhances safety in the system, since any overcurrents or fault currents that might arise at one side of the inverter does not automatically affect the other. Isolation is given by the presence of a transformer working either at low or high frequency. This allows the two parts of the system to be electrically decoupled. The inverter of the transformerless type clearly does not feature galvanic isolation. Residual current monitoring, as we have seen previously in this video, is present only in the transformerless inverter, and it is useful to detect the presence of any undesired residual current flowing inside the device. If the transformer is used, monitoring cannot be performed. Another aspect to consider is the electromagnetic radiation that may interfere with other devices in proximity of the inverter. When a transformer is used, the electromagnetic compatibility is usually achieved and the radiation can be kept under control. On the other hand, the transformerless type can possibly emit radiation that can interfere with other devices functioning or even cause physical damage. Since the first PV inverters were designed for crystalline silicon modules, it is interesting to check whether these can also be adopted for thin film modules. This is mainly due to the fact, as we will see in the next videos, thin film modules are subject to some deterioration phenomena, such as the corrosion of the transparent conducting film. It appears that when a transformer is used, the usage is ensured for thin film modules, while some issues may arise when adopting an inverter without transformer. Another crucial aspect when a system design is performed is the size and weight of the inverter, especially for standalone and rural applications. As we mentioned before, the main transformer is particularly bulky and heavy, while the high-frequency transformer is a smaller and lighter device. The transformerless inverter is clearly preferable if the PV system requires a lightweight and small-sized device. Lastly, the efficiency of different types of inverters must be taken into account. The transformer, even though reliable and highly efficient, is a cause of ohmic and magnetic losses in the inverter. These losses are proportional to the quantity of material used for the transformer, such as the core and the copper cables. For this reason, the heavier and the larger the transformer, the higher the losses are. This is also a reason why the transformerless inverter is often chosen in a PV system design. To sum up, in this video we saw what are the different parts that practically form an inverter. First, we had a look at the transformerless type. Then we saw the inverter with either mains or high-frequency transformers. In the last part of the video, we had an overview of the differences between the three types of inverters that can help you choose the appropriate one when designing a PV system.